Okay, so can we start now?
Yeah, sure.
Okay, I'll just give a brief introduction for everyone.
Yeah.
Krishna Sir has completed his PhD in mathematics at the Chennai Mathematical Institute in India and is currently a postdoctoral researcher at KTH, Sweden. His mathematical interests lie in combinatorics, the art of finding patterns and counting possibilities. What excites him most are problems that are easy to state but deep to think about, the kind that invite curiosity rather than complicated machinery. Over to you, sir.
Thanks for the very kind introduction. And yeah, so today we are going to talk about, as Nidhi mentioned, what I like a lot is combinatorics and counting problems. So today we are going to be mostly looking at counting problems. But rather than, so last time that I talked at Roots, I fixed one problem and spent the entire time talking about that. And it was quite an interesting problem, I think. But now, hopefully, what we'll try to do is look at different kinds of problems if the time permits. And what I would like to do is give an idea about how one would approach a counting problem and what are the things you could try. Of course, there is no general, I don't know, method to solve any counting problem, but maybe some sort of ideas that could help in counting problems. Okay, so before we start, I thought first off I should just give a sort of vague definition of what a counting problem is. And it is basically something like this. So you are given a bunch of objects and you are asked to count them. Of course, this is a very, I don't know, simple sentence and maybe doesn't give much idea. But basically, these types of objects that we'll be looking at can be very different. Their questions could be like, oh, how many ways can you distribute 35 chocolates among 15 people? Or it could be something like, how many numbers from 1 to 100 are divisible by 7? Basically, you're given some property or possibility or something, and you're supposed to figure out how many objects satisfy this property or the conditions given to you. So this is usually the kind of counting problem that one sees. And before going forward with some concrete problems, I just wanted to see if anyone has any opinions already about counting problems. Do you have any experience with counting problems? Do you have anything good or bad to say about counting problems? How do they relate to the other problems that you have seen? So, if anyone does have any opinions, maybe you can raise your hand and the volunteers can choose someone to say something. Okay, so there is someone. So
Can you hear me?
Malolan, if you want.
I don't know. They just ask you to count. Like you're given a few constraints, and then you just have to count how many ways you can do something. Like maybe like arrangements and or whatever.
But do you have any opinion? Like, do you like these kinds of problems? Do you not like them? Do you think they're more difficult or less
Yeah,
difficult than others?
I obviously like the easy ones, and maybe I would hate the hard ones.
Okay, yeah, that's a nice opinion to have. I too shared that opinion for a long time. So thanks for that, Malolan. Anant, do you have something to say?
Yes, sir.
Hmm.
I think counting problems are fun, and I think I would like them more if they are challenging.
Okay, so that is nice to hear. Um, is there anyone else who has something to say? Yeah, Vikrant.
Sir, basically both of Malolan's and Anand's points together.
No, okay. Okay, so there are, so what I've heard so far, there are people who, at least the three of you, who seem to maybe like counting problems, and some are challenging, which could be annoying but maybe fun. To be honest, when I was in school, I was very scared of counting problems because I always thought I'm definitely going to make a mistake. I'm not going to be able to count stuff properly. But as I did more and more math, I fell more into combinatorics because, I mean, the one thing I like about combinatorics is that you don't have to learn much background, right, to start working on combinatorics. They're the type of questions where you don't need to know like high level math stuff to understand the problems. And that is one thing about them that I really like. So hopefully now as we solve some problems, maybe your opinions about counting problems will change. Maybe you'll find them more annoying. I don't know. Hopefully less annoying. And what the plan is to just look at some counting problems and maybe along the way give some ideas of what one should try when one encounters a counting problem. But before doing that, so the problems that I talk about may be for some of you something that you have already seen or might be simple for you, or maybe you're just not interested in these problems. So I am sharing in the chat a Google Drive link to a document that I have made with some other more challenging problems. So if you are not very interested in what's going on in the session, you can go to that. But hopefully, maybe you'll just listen for maybe the first 15 minutes and see how you feel about the session, and then you can check out that document if you want. Okay, so let us now start with the math. So the first thing we're going to be looking at is, maybe I should first make a definition just so that we don't so that there's not much confusion. So this maybe is a definition that people might have opinions about. So at least for me in these sessions that we have, natural numbers are the numbers 1, 2, 3, 4, and so on. Basically, we're not going to assume that 0 is a natural number. Some people have strong opinions about that for some reason. But so for this talk, when I say a natural number, I just mean a number 1, 2, 3, 4, these counting numbers. Okay? So the first problem we're going to be looking at is, so you are given, let's say, the number 5. How many ways, or let's say how many pairs A comma B of natural numbers are there with A plus B equal to 5? Okay. So this is the sort of problem that we will be looking at. So I'll give you a number. So we're just looking at a specific example first. So here the specific number that we have is 5. And the question is to figure out how many pairs of natural numbers there are whose sum is 5. So for this particular problem, I'll just write down what these pairs are. And then we'll try to see in general what we can do. Okay. So for example, here, the pairs are, I could maybe do something like 5 is 3 plus 2. So maybe 2 comma 3, that would be a pair. So it's a pair of natural numbers whose sum is 5. I could also do maybe 4 comma 1 because 4 and 1 are both natural numbers with sum 5. I could also do maybe 3 comma 2, just the sort of reverse of that. That of course will also have sum 5, and 1 comma 4. Okay. So these are the sort of objects. So for this particular number 5, the number of pairs of natural numbers with sum 5 is exactly these 4. And so for this question, the answer is 4. So is there anyone who disagrees with what I have just said? Okay. So hopefully everyone is on board for this. So of course the problem is just, okay, this was for a specific number 5, but what if you are just given some random number? Then how many pairs will be there with this property? Okay. So let us maybe start making a table of this. So n is the number that I'm going to be picking, and then the number of pairs. Okay. So what we have got at least is that for 5, there are 4 pairs, which seems that nobody has a disagreement with. But now I want you to fill up the rest of this table. Let's say for 4, what would it be? For 3, what would it be? For 6, what would it be? For 7, what would it be? And so on. So does anyone have any ideas of what these
And
numbers would be?
one.
Please don't just
Okay.
speak out your answer. Wait for a volunteer to decide someone whose hand is raised, and then so that everyone has a chance to speak.
Sir, you can call out to the students who raise their hands.
Oh, okay. Yeah, sure. I'll do that. Yeah. So, Kyra, do you mind?
My answer was n-1.
Okay. So basically, you're saying whatever n is, n minus 1 would be written. So this would be 2, this would be 3, this would be 5, this would be 6, right?
Yeah.
Okay. So is there anyone who disagrees with this? So raise your hand if you disagree with this. Okay, so it seems that everyone is fine with this. So now the question is, yeah, so Viren, do you have a question?
Yeah, I disagree with this because this works for odd numbers, but for even numbers, it should be a comma b, but it comes as 2 and 2, but that won't be a comma b. It should be two different numbers, I guess.
No. So we won't insist that the numbers are different.
Oh, then it's
I
fine.
mean, okay. So Nandita, you have a.
Should the numbers only be natural numbers or can 0 also be included?
For now, we will stick to natural numbers. We will eventually come to what happens if we allow 0. But for now, we are only
Then I
looking at
don't have
natural
an
numbers.
objection, sir.
Okay, thank you. Okay, so it seems that everyone at least agrees that these are the numbers. Does anyone have a proof? Does anyone want to present a proof of why this is the case? So, Vikrant, could you?
Yes, sir. So, like, basically, my proof is like checking case wise for each number, sir. You cannot start with a 0 because it will end with because 0 is not natural. Like, if example, we take a number 3. We can only we find from 1, we see all the numbers from 1 all the way up to 3. If, 1, there's a pair, 2, there's a pair, 1, but 3 leads up to 0, sir. So it doesn't work. So that's
Okay.
why there are two solutions. If you want to say Cn, we can say that 1 plus n minus 1 equals to n, 2 plus n minus 2 equals to n, and so on, so forth. Then n minus 1 plus n, 1 is n. But if we take n, then n minus n is 0, so there is only n minus 1 solutions.
Okay, thank you. Perfect. Does anyone have any problem with this proof as to why there are exactly n minus 1 possibilities? So, Shivansh, Do you have a problem with this proof? Okay. Okay. Okay, so basically this was a sort of hopefully simple question just to start you off with this kind of problem. Okay, so you're just given a number n. So here first we looked at 5, but then we saw in general n, and you're supposed to find the number of pairs a comma b that have the property that a and b are both natural and their sum is n. Okay? And then we got a proof over here that that number must be exactly n minus 1. And in fact, we have explicitly written down what these n minus 1 possible pairs are. Okay? So there was someone who asked, okay, is it okay to give 0? Okay? So that was a good question because it is sort of the first step that I would suggest for anyone who's trying to solve a counting problem, which is understand the objects. Okay? So, of course, this was quite a simple problem, but as we look at other problems, what would help is that you try to figure out what these objects are. You play with the objects for small numbers n and make sure that you understand the objects that you are counting. Because, I mean, if you don't understand what you're counting, then of course it makes it difficult to go forward. Okay? But now let us try to see what else we can do with this type of problem. So of course, the next sort of maybe natural problem would be, so now you are given, let's say, 6. How many triples A, B, C of natural numbers are there with A plus B plus C equal to 6? Okay? So the first problem, we just tried to see how many pairs there are. But now, of course, we want a slightly harder problem. Now you have to count how many triples there are with sum equal to 6. Okay? So Kamal, do you have a sorry, Kamal, I can't hear you. Is it my problem or I mean, can others hear him? Like
No, sir, not well.
okay. Okay, Kamal, I think you have a problem with your mic. Maybe you can
I
try
think
to
he
fix
unmuted
it.
just now.
Sorry?
Oh, okay, I think yes, there's an audio issue.
Sir, Kamal is
Yeah,
unmuted, sir.
yeah, but I can't hear what Kamal is saying. Kamal, I think there is a problem with your mic. Maybe you can try to fix that. I'll ask someone else in the meanwhile. Okay, so Madhusudan,
Yes, sir.
Madhusudan, can you, yeah, can
Yes, sir.
you?
There are 6 different pairs for this
Okay.
specific question.
So can you tell me what these pairs are?
Yes, sir. First
Yeah.
pair is 1 plus 2 plus 3.
Hmm. Hmm.
The second pair is 1 plus 3 plus 2.
Hmm.
The third pair is 2 plus 1 plus 3.
Hmm.
The fourth pair is 2 plus 3 plus 1.
Hmm.
The fifth pair is 3 plus 1 plus 2.
Hmm.
And the last pair is 3 plus 2 plus 1.
Okay, thank you, Madhusudan. Is there anyone who objects to this, who thinks maybe uh, there should be fewer, there should be more? So, Anand, can you?
10,
There was an echo, I think.
10 number of triplets.
I'm sorry, Anand. I think there is an echo, so it's hard to understand what you're saying. Okay, so I mean, let me ask someone else. Tarun, do you have?
Sir, can the value of all the variables be the same?
Yeah. So there is no restriction. Like for example, that's why all these numbers we had the similar sort of thing. Because in 4 you would have
10
1,
number of
3, 2, 2.
So we can have another pair 2, 2, 2.
Okay, so 2, 2, 2. Anything else?
No. Thank you, sir.
And I think someone is there with the mic on, so we can hear the background noise. So can you please switch off the mic if you are not talking? Okay, so Deepika, can you tell me?
So 114.
Okay, 114.
411.
that total 10 number of pairs.
411. Please only speak like when I call your
141.
name down. 141.
Yes, sir, that's it.
Okay, so does anyone object to this? Does someone want to add any more or remove some or do anything? Kamal, have you fixed your mic? Can you try speaking? I'm sorry.
I think Kamal have any internet issues. Can you ask to someone else?
Yeah, sure. No, I just wanted to confirm once more. Yeah, so Bhargav?
Okay.
Sir, just a clarification here. A, B, C doesn't it refer to three different natural numbers?
No, it doesn't. A, B, and C, the only restriction is that they have to be natural numbers. That's it.
Okay, sir, that's the only clarification.
Okay. So hopefully no one has an objection with the fact that here for 6, if we fix 6, then the number of triples of natural numbers with sum equal to 6 is 10. Right? So what now I would suggest that you do is for other numbers, exactly the same thing I want you to try. So for example, for 6 over here, we got 10. So what about 7, 5, 4, 3, and so on? Maybe I'll space them out better. So what I want you to try now and see is for these different numbers, let's say for 4, how many triples of natural numbers are there with sum equal to 4? Similarly for 5, 3, 7, and so
Sir,
on.
sorry, sir, I spoke out of.
Yeah. So Ayush, what do you want to say? Ayush, your hand is raised. Do you want to say something?
Sir, I prove for A plus B plus C is equal to N.
Okay, I
Number of
mean, so if you have that proof, then you'll be able to fill in these numbers, right? So for example, for 5, what is the number of triples?
6, sir.
6. Okay. So for 4, what is the number of triples?
3, sir.
3. Okay, so thank you, Ayush. I'll come back to your general answer in a while. But before that, let's say Arav.
Hello, sir. Just a gentle reminder for you. We are left with the 5 minutes, but if, as I can see, there are some doubts are remaining, so we can stretch up to our 5 minutes more. if you wanted to.
Oh, I mean, the session just started, right?
Sir, isn't this
Hello?
till 6 o'clock?
Isn't the
Session
session
is
6
till
o'clock?
6
Oh,
o'clock.
sorry, my bad.
Yeah,
It's 6 o'clock.
yeah, sure.
Sorry,
Okay,
sorry.
so
My bad.
yeah, no worries. So Araf, what did you want to say?
So I found a pattern. It's, I think, the n minus second triangular number.
Yeah, okay, that's great. But can you first tell me what I should write down for 3 and 7?
So 3 should be 1
Yes.
and 7 should be 15.
Okay. So we'll come to the general answer in a while. But before that, I just want to ask whether anyone, first off, does not understand what we are doing, like where these numbers are coming from, or if there is someone who disagrees with any of these values, who thinks maybe, oh, this should be 18 or something like that. Hmm? So is there someone who does not understand what we are doing or has an objection? So, Abhyudya, do you have a...
Sir, I don't understand how we got these
Okay,
numbers.
okay. So for example, for n equal to 6, what we want to do is we want to find all triples of natural numbers. So that means something that looks like this. So you have 3 natural numbers. They don't have to be distinct. You can repeat the same number. That's fine. But it is 3 natural numbers whose sum is 6. Okay? So for example, here 1 plus 1 plus 4 is 6. So we include this triple. Similarly, we include this triple 2, 3, 1 because 2 plus 3 plus 1 is 6. Okay? So for n equal to 6, we just write down all the possible triples of natural numbers whose sum is 6. Okay? Where we are allowed to repeat these natural numbers, but we care about the order of the numbers. For example, that's why this 1, 2, 3 is different from 1, 3, 2. It is the same 3 numbers 1, 2, and 3, but we do care about the order in which they are written. Okay? So that is the things, those are the things that we want to count. Triples of natural numbers with sum equal to n, and in this case here we are looking at n equal to 6. So is that fine, or do you...
Can you repeat the last line where you said the n is equal to?
Yeah, so n over here, so the reason that I'm writing n in this table, it is just the sum. So here for n equal to 6, I am getting 10 because there are 10 triples that we have written over here of natural numbers where the sum is 6. So that is what this n is representing. Okay, so it is just the sum of the entries in the triples. So I hope that is fine. If you have any other... Okay, so does anyone else have any other questions about what these numbers are, or I mean, why are we writing these numbers? What do they count? Or has any objection with any of the particular numbers written over here? Okay, so Arav, are you raising your hand because you don't agree with something that was said or written, or do you
No,
want...
sir, I think I have a proof of this.
Yeah, okay. So hold on 1 minute. So if there are no more questions, then please. So Madhusudan, are you also raising your hand because you have a doubt or because you have a...
Sir, I think I have a generalized formula.
Okay, okay. So now, if there are no more doubts, please raise your hands if you have noticed any patterns or you want to make any comments about how this would work in general. So Asma, could you please...
Yeah, I had seen that it was like depending on n, if n is like for example 7, then it would be n minus 2 into n minus 1 divided by 2.
Okay, so one claim is number of triples for n is, so you said I think n minus 2 into n minus 1 divided by 2.
Yeah, which is the n minus 2th triangle number.
Okay. So do you have a reason for saying this, or
No,
is
I'm
it a
trying to think.
pattern?
Yeah, it's just a pattern. I'm trying
Okay,
to prove it.
okay. But yeah, hopefully it'll match at least for the values that are written. So let's see who else. Maybe Arav, do you have something you want to say?
Sir, it was the same as before the proof. I'm just keeping my hand up for now.
Yeah. So can you go? So first of all, do you agree with this?
Yes, sir.
Okay. So, but you do have a proof as well.
Yes, sir.
Okay. So can you talk us through a proof?
Yes, sir. So the same as before, we can try to list all the triples. So let's first start with A equals 1. So 1, B, and C. And we know that for B and C, 1 plus B plus C to be N, B plus C needs to be N minus 1.
Okay.
So number of triples 1, comma B, comma C is the same as the number of triples B, comma C such that B plus C is N minus 1. And there are N minus 2 triples this way.
Okay. So number of such triples is number of pairs B comma C with some n minus 1, and this is exactly n minus 2.
Yes, sir.
Okay.
So then we can do the same for 2, comma B, comma C. Here B plus C
Okay.
needs to be N minus 2, and there are N minus 3 ways to do this.
Minus 2. Yes.
So we can't go down to N minus 1, comma B, comma C, since that would need either B or C being 0. So the lowest we can go is N minus 2, comma 1, comma 1.
Okay, so just so that let me just add one more step before going to the final. I'll just write it down for 3 also, just in case. So if the first number is 3, then B plus C has to be n minus 3. So the number of such triples correspond to the number of pairs B comma C with some n minus 3. So there are n minus 4 triples. And then the last one, what did you say? Can you repeat? Sorry.
We cannot have N minus 1, comma B, comma C because that would involve either B or C being 0. So the last thing we can have is N minus 2, comma B, comma C, which means that B plus C is 2. And there's only one way to do this since B and C both have to be 1.
Yes.
So in total, the sum of all of these number of ways is 1 plus 2 plus and so on till n minus 2, which is just n minus 2 triangular number, which is n minus 2 times n minus 1 all over 2.
Yes, so let me write down what you said. So the total number of triples is 1 plus 2 plus and so on to n minus 2, which you are saying is equal to n minus 2 times n minus 1 by 2. Okay. So first off, is there anyone who has a doubt about this proof, does not understand what is happening? Yeah. So please raise your hand if you have any questions about this proof that you don't understand, for example, where this came from, where this came from, or this came from, like what is happening in this proof. Okay, so if everyone follows, then I guess everyone agrees with this sum as the number of triples. Madhusudan, do you not agree or do you have a...
Sir, I agree, sir, but I have a better, but I have another, what should I say? Another formula for to find this. Can I
Okay,
share it,
yes. So,
sir?
yeah, 1 second. I'll come to you next. But, okay,
Yes,
so
sir.
then I'm assuming everyone understands where this formula comes from for the total number of triples. Okay, so if everyone does understand this formula, this I don't know if everyone knows why this sum of numbers from 1 to n minus 2 is the same as this expression over here. So that for now I won't talk about. Before I talk about this, I want to hear what Madhusudan has to say.
Yes, sir. Sir,
Yeah.
I generalize this formula to make it smaller. The formula I'm sharing is n minus 1 chooses 2.
Okay. Let's see. So, is there anyone here who does not know about like these choosing numbers like n choose k, what it means? Is there anyone here who does not know what these are? Okay. I am surprised. I thought that comes quite later in the. Malolan, yeah,
No,
you
sir.
have not seen these.
Then I have a general formula for like the whole thing. If you
Okay,
want me
yeah,
to
yeah,
generalize
yeah,
also.
yeah. But so everyone here knows what these, like for example, what n choose k, those numbers. You're all familiar with that.
Sir,
Yes,
we learnt about n choose k in the last class, last roots class. That's why.
Okay. Yeah. Then sure, that's fine. Yeah. Okay. So, Madhusudan, so you are saying what? That this number is, what did you say?
N minus 1 chooses 2.
Yeah. And how did you write that? Is it with the C like this and minus 1
Yes, sir.
C2, or did you
Yes.
write it like this?
I wrote in the second way, sir.
This way.
Yes, sir.
So that's how you were taught in the previous roots class?
Yes, sir.
Sir, we were
Okay,
taught
yeah,
in
anyway.
both ways.
Okay, but I like the second one. I hope everyone is fine if I use the second one. Okay, so you are saying that this is n minus 1 choose 2. But your proof, Madhusudan, was the same as this one, or was it a different kind of proof?
What should I say? It's actually similar to this proof, sir. So,
Okay. Yeah, okay. So, I mean, if you have seen these, what they call binomial coefficients in the previous.
Yes, sir.
Okay, so if you have seen binomial coefficients, then what did you learn that they are? What do they mean? So, for example, what does n choose k mean? So, can someone? I mean, if you have learned this, does anyone remember what this means?
n factorial upon
So,
c factorial into n minus k factorial.
so who's talking? Is it Kamal?
Yes, sir.
Okay. So nice to hear that your mic is working. Yeah, but okay, so you learned a formula for this, but did you learn any meaning that it had?
Out of n articles, we are choosing k articles.
Okay, so this is the number of ways of choosing k things from n things. Okay, so hopefully this is what you all saw in the previous uh, roots thing. Okay, so one expression that we have got for this number of triples So let me write that down. So the number of triples A, comma B, comma C of natural numbers with A plus B plus C equal to N is N minus 1 choose 2. Okay, so at least this is what Madhusudan has suggested. And I will say that this is correct. But now, does anyone have a proof of this without going through using this definition of N choose something? For example, N choose K is the number of ways of choosing K things from N things. Okay? So what this statement over here is saying is the number of ways to write N as this sum A plus B plus C, where this A, B, and C are natural numbers, is N minus 1 choose 2. This number N minus 1 choose 2, apparently you have learnt in a previous roots class, means exactly this. It is the number of ways of choosing. So this is the general meaning. So for N minus 1 choose 2, it is the number of ways of choosing 2 things from N minus 1 things. Okay? So what I want you to think about now is, can you see this directly? Can you convert this problem, finding these number of triples, change this to a problem where you're just choosing 2 things from N minus 1 things?
Sir, I think I have a way to do this, like using the choose.
Who is speaking now?
Sir Malulan.
Okay. Yeah, sure. Can you go ahead?
Yeah, there are multiple ways you can do this, but we can just build on with from the point where the previous solution was that. So there are you once you choose two numbers, two natural numbers, less than n, there's only there's only one possible solution for C. So let's say if you choose A and B, then there's only one possible solution for C.
Okay.
So all we have to do is choose the values for A and B in the range of 1 to n minus 1.
Okay. So what you're saying is to construct A, B, C, I choose A and B from 1 to up to n minus 1. And this, of course, I can do in n minus 1 choose 2 ways. And you're saying that will specify what C is, and hence we have the answer. Is that what you're saying?
Yes, sir. But there's another way also to think of this.
No, 1 second. Let's go through this first.
Sir,
So
there's a mistake in the thing.
who's speaking now?
Vikrant, sir, Vikrant.
Okay,
Sir,
so
it should
Vikrant,
be
can
n.
you?
Sir, it should be n minus 2, sir, not n minus 1. Up to n
Oh, so you're
minus.
saying this formula is n minus 2 choose 2.
Not in that part. In the I choose A and B from part.
Oh, you're
Because,
saying this should be n minus 2.
yes, sir. Because n minus 1 plus, if we choose n minus 1 and 1, then n minus 1 plus 1 is n.
So Malolan, do you agree with what Vikrant is saying?
Yeah. He's right.
But
Yeah, there's a mistake in that.
okay, but so you agree with the correction to the mistake as well, which is just okay. Now instead of n minus 1, you write n
Oh,
minus
yeah,
2.
the general formula is itself wrong. It's supposed to be n minus 2 choose 2.
Oh, so now you're saying this is supposed to be n minus 2 choose 2.
Yeah.
Okay, so now let's go back to the table that we have.
Sir?
So we have these values. Let us write down, let's say over, let me move this. So this is the P moved. So this is number of triples, and one candidate that we had was n minus 1 choose 2. Another candidate now is n minus 2 choose 2. So n minus 2 choose 2 for 4, what would you get? So number of
Oh
ways to
yeah,
choose.
that's one. I mean that's
Yeah,
two. Oh sorry,
this is
that's one.
what
Yeah, that's
2.
one. That's one.
No, I mean, I don't know. I'm actually just listening to you. So what should I do? So if n is equal to 4, you get 2 minus 2 choose 2. So that is 1. Okay. So definitely this formula is not correct. So does anyone disagree with that? That this formula could be correct, n minus 2 choose 2. So let's write down n minus 1 choose 2. Right? So what is 3 minus 1 choose 2, which is 2 choose 2. So that is
Won't it be
1
4 minus 1 choose 2 for the second
over
one?
here, right?
Yeah.
Yeah, so here 4 minus 1 choose 2 is what? 3 choose 2. How many ways can I choose 2 things from 3 things?
3.
3.
Yeah, 3.
Yeah. Now, how many ways can I choose 5 minus 1? So 4 choose 2. How many ways can I choose 2 things from 4 things?
6 ways.
6 ways. And then, I mean, definitely we know this is not the answer then, right? N minus 2 choose 2. N minus 1 choose 2 might be the answer, but also maybe it's just agreeing for the first 3 terms and then might disagree at the, I don't know, 45th term or something. Yeah.
Sir,
Okay.
sir, this is Madhusudanan. I have a proof that n minus 1 choose 2 is the correct formula.
Okay, but okay, so I will listen to your proof. I promise, Madhusudan. But
Sir,
I forgot. Are
I
you the one who
also have a
suggested?
proof.
Uh,
Sir,
who's speaking?
sir, Kamal, I also have a proof.
Yeah. So if you want to say something, then just raise your hand. I'll call on you. I mean the raise hand of the in the Zoom. Yeah, yeah. Okay. So, but before that, Madhusudan, before the proof, like, so you don't agree with this, what was said over here, right?
Yes, it feels a bit, what should I say, bit elongated and bit confusing.
Okay. So then can you tell me what you want to, so now you are proving that, you're proving this fact, right? That the number of triples A, B, C with, of natural numbers with some n is n minus 1 choose 2.
Yes, sir.
Yes.
So,
Okay. So can you
yes, sir,
tell me?
let me start.
Yeah.
Okay. Sir, first I take, as it's stated in the original proof, a plus b, the first proof, a plus b plus c is equal to n. Now I take a variable x is equal to a minus 1, a variable y is equal to b minus 1, and a variable z is equal to c minus 1.
Okay.
Sir, is it okay?
I mean, yeah, continue.
Okay. So now we can, now a minus 1 is either greater than or equal to 0. B minus 1 is either greater than or equal to 0, and c minus 1 is also greater than or equal to 0. So a is greater than or equal to 1, b is greater than or equal to 1, c is greater than or equal to 1. So next, now x plus 1 plus y plus 1 plus z plus 1 is equal to n.
Okay.
So x plus y plus z is equal to n minus 3.
Okay.
Next I'm taking another set.
Okay.
Now a1 plus a2 plus a3 till a k is equal to m.
Okay. Why are you doing that?
To derive an to derive an answer for this formula, sir. It actually worked, sir. That's why I'm trying it, sir. I'll explain it to you, sir. So,
Okay.
A1 plus A2 till AK is equal to M.
Okay.
So, by that we can get M plus K minus 1 is equal to K minus 1. Sure.
Okay, Madhusudan, I think you are trying to do something much more general. So let us not talk about that now. All we are trying to do is now count the number of triples with sum equal to n. Okay? So maybe we can look at your solution when we are talking about the general problem that I'm heading to. But for now, let's say, Ayush, do you have something to say about this statement written over here?
Yes, sir. I have different way to add 1 plus 2 plus till n minus 2.
So you're talking about this one over here.
Yes, sir.
Yeah, so what do you want to do with this?
First, this is
Sorry.
natural number. First, n minus 2 natural number. So sum of first n natural numbers is n into n plus 1 by 2.
Okay, yeah, so that is a formula that you already know. That's what you're saying.
So I put n is equal to n minus 2.
Okay, yeah, okay.
That is
Yeah, sure.
sum is n minus 2 into n minus 1 upon 2.
Yeah, okay. Okay, so let's see. So now, hopefully at least, so let's see. Let's forget about this part and this part. But is there anyone who does not understand this part? That the number of triples is just 1 plus 2 plus 3 up to n minus 2. So, Vikrant, are you raising your hand because you don't understand this?
No, sir, I just wanted to tell everything was correct, sir. About the general say that n minus 1 choose to is correct. And also, we have to choose 1, 2 up to n minus 2, sir, that A and B thing. In Malone, proof. Because
Okay.
n choose 2 is basically n factorial times 2 factorial n minus 2 factorial, which we can cancel out the n minus 2 factorial part. It will become n times n minus 1 by 2. But then the formula for sum of first n numbers is n times n plus 1 by 2. So the statement, the general statement is n minus 2 choose 2 is wrong.
Yeah, yes, but that we already sort of figured out, right? We just wrote down the number and saw that it is not matching.
So, but anyways, I was saying with the definition.
Okay, yeah. Okay.
Sir, I have a different
So-
proof actually.
Who is speaking now?
Madhuran himself.
Okay. So different proof of what?
For using the combinatorial way, like using NC2.
Okay. So can you tell me?
So let's forget the condition that it's let's include 0.
Okay.
So if we include 0, later we can remove zeros, but let's include zeros in the solution set. Now,
Okay.
if we actually do, if we consider all the possible options for, so let's partition let's consider it to be n people, and we'll start partitioning them.
Okay.
So if we add all of them, so if we partitioning them, it should be 1 less than 3. So like if you put partitions, there should only be 2 partitions. So each A, B, and C will represent 1 partition each.
Okay.
So now so let's add the partitions and all the objects. So we get n plus 2. And out of these, we just need to choose the two partitions. So we totally have n plus 2 objects, and we have to choose two objects from that.
Okay, so Malolan, I think you have a very good idea. So let me just try to write that down for everyone. So this is one of the sort of things that you probably have to do when you're asked to solve these types of problems, when you're asked to count something. So one of the very useful tools when trying to do any counting problem is you change the problem to a form that is easier to work with. Okay. And in this case, especially when we know sort of or guessed that the answer would be something like this, it would be nice if we can write down these triples where there are n objects or whatever, n minus 1 objects, and we are having to choose something. Okay? So one way in which you can do that is as follows. Okay? So I'll just do it with an example. Let us say n is equal to 6, and we are looking at, say, let's say 1, 4, 1. Okay? So one way in which you can represent this is as follows. So you have split 6 into 3 parts. Okay? The first part is 1, the second part is 4, the last part is 1 again. Okay? So one way in which you can look at that is you write down or you draw 6 balls. Okay? So this represents the number 6 over here. So that's why we have drawn these 6 balls. And we're going to split it into 1, 4, 1. Okay. So the way we represent the split is just, okay, we'll draw a line after the first ball. So that represents this 1 over here. Then next we have 4. So that we will represent as these 4 balls over here. So then we'll draw a line over here. Okay. So this represents exactly 1, 4, 1. Okay. So let's look at another example. Let us say again n is equal to 6, and let's say 2, 3, 1, or maybe 2, 1, 3. Okay. So how we would represent this is, again we have 6 balls, 1, 2, 3, 4, 5, 6. And how would we represent this? We want the first part sort of before this first partition over here, we want 2 balls. So we'll break this over here after the first 2 balls. So that is precisely because we are trying to capture this first 2 over here. Now the next part we wanted to have only 1. Okay, so only 1 ball. So it should just be this ball over here. So the next place I'll break is over here. And finally, you see this last 3 corresponds to these 3 balls over here. Okay? So what are you doing? You have these n balls over here, and you're sort of placing these bars to indicate how you're splitting it up into 3 parts. Right? So now, okay, is there anyone who does not understand this sort of way of reimagining these triples of numbers? Okay, so if everyone is on board with this, then now the question is again, so if you have n equal to 6, and I want to split it into these 3 pieces, what I have to do is just decide where I want to put these bars. Okay? So now can someone tell me where this formula comes from? So Asma, can you
Yes,
tell
sir.
me?
Can you scroll down? Can you go back to the picture?
Yeah.
Yes. So the number of gaps here is 6 minus 1, which is 5. So we'll be placing the bars in these gaps. And we have to place 2 bars to get 3 numbers which add up to n. So we have to just do n minus 1 choose 2, which is where the formula came from. So we're just finding out where the bars have to be placed, and the number of gaps will be n minus 1. So, yeah.
Yeah, so that is a perfect answer. So is there anyone who disagrees with this or does not understand this answer? So as a particular example, so let's say n is equal to, I don't know, n is equal to 8. So we have 8 balls, 1, 2, 3, 4, 5, 6, 7, 8. I maybe drew the balls too big. Now what Asma said was just, so since you have 8 balls, you have these sort of 7 spots between them, these 7 empty places between them. Now I want to put the 2 bars, right, to distinguish. So before the first bar is my first part, between the first and second bar is my second part, after the second bar is my third part. So for example, I just have to choose 2 places to put the bar. Let's say I have chosen this place over here, let's say this place over here, and this place over here. Then the corresponding triple is precisely 2, 3, 3. Okay? Because there are 2 balls before the first bar, 3 balls between the first and second bar, and 3 balls after the last bar. Okay? So, to be honest, I did not know that you would already have seen binomial coefficients earlier, so I sort of had to change what I was planning to do. But this sort of, whenever you see binomial coefficients, at least I would suggest to try to reshape your objects into ones where you can do actually choosing. Okay? So that is exactly what we had to do in this case. Okay? So we had these n balls and we had n minus 1 slots between them. And we had to choose 2 places to put the bars. So that then we have now split these balls into 3 pieces. And the number of balls in each piece correspond to the numbers in the triple. So is there anyone who does not agree with this or has questions about this? Okay. So if there are no questions, so I'll just write down again finally what all this has proved. So the number of triples A, B, C with A, B, C natural and sum n is, no need to write sum n, A plus B plus C equal to n is n minus 1 choose 2. Okay. So that is another thing. So when you, for example, when, I'll have to scroll back quite a bit. So when you, for example, saw this sequence of numbers, a lot of you already knew that these are the triangular numbers. Okay, and we in fact got a nice proof, which was this. I forgot who gave this proof, but this, okay, if the first part is 1, how many are there? If the first part is 2, how many are there? The first part is 3, how many are there? And so on. You keep counting. And then you get this formula 1 plus 2 and so on. Okay? So that is a completely valid proof and in fact a very good proof. Okay? So that gives you one answer, which is that the number of triples is 1 plus 2 plus 3 and so on up to n minus 2. That gives you one answer. But of course, since you have already seen these binomial coefficients, some of you suggested that n minus 1 choose 2 is the answer. Okay? So one way to do this is when you see that the answer is something like this binomial coefficient, don't just stop and say, okay, this looks like the binomial coefficients because I computed, let's say, the first 17 terms and it all matched this binomial. So I'm happy and I'm done. But try to prove it. Okay? So this is the next thing that I will say about counting problems. So this I think is step 2. Play with examples and look for patterns. And of course, it will be great if you do find a pattern. Like for example, a lot of you did figure out that these are triangular numbers. But also try to prove the pattern. Okay. So we saw one proof earlier for these numbers, which is the 1 plus 2 plus 3 and so on. And Asma also noticed another proof for the n minus 1 choose 2. Okay. So the reason I'm saying this is because there are some problems in mathematics where when you play with small examples and you try to notice patterns, things all seem very nice, but they can eventually break. Okay. So I am sending in the chat a YouTube link to one such problem where it initially seems like there is a very nice pattern going on, but later it breaks. So always when you see a pattern, don't just be happy and stop. I mean, of course, you should be happy that you have found a pattern, but always try to prove that the pattern you have found is actually true. Okay, so this is exactly what we did in this case. Okay. So now does anyone have any questions or even like does not understand what we are talking about with these triples of numbers, binomial coefficients, and so on? Okay. So if there is nothing, then I guess you can sort of figure out what we're going to do next. Initially, we talked about, so we have 10 minutes left. Yeah, sure. So initially we talked about like, okay, if you have a number, how many pairs can I find? Like 2 numbers that sum up to that number. Then we looked at triples of numbers. And of course, now the question is, what next? So 4 numbers. So whatever it's called, a quadruple of numbers. So the next thing we have to think about is, so let's say, so for a number n, how many quadruples? Or you can just say 4 pair, whatever you want. A, B, C, D of natural numbers are there with A plus B plus C plus D equal to n. Okay. So this is sort of, I mean, this is what we have been doing. So we started with first how many pairs of numbers there are with this property, then how many triples of numbers there are. Then of course the next natural thing is what if now I have 4 numbers. Okay. And again, just so that everyone is clear, we will look at an example. Let's say n is equal to 5. So for n equal to 5, maybe you would have things like 1, 1, 1, 2, or 1, 1, 2, 1, or 1, 2, 1, 1, or 1, 1, maybe 2, 1, 1, 1. Okay. So this sort of thing. How many quadruples of numbers are there whose sum is equal to n? Okay. So this, of course, I mean, okay, does anyone have, of course, what I would suggest that you do is write down for the first few initial values of n, see what these numbers are, and then see if you can notice any pattern. But is there someone who already wants to make some conjecture or something about what these numbers are? So I see a lot of hands raised, so maybe Anantajit, do you want to say? Oh, hand went down. Okay. So maybe Kyra, do you want to say something?
Sir, can we use the previous question method of n minus 1 C3?
So you want to, so maybe I'll write it over
Because the number
here.
of gaps are the same and we need to place the same number of bars. So we can
Oh,
technically
how many bars are you placing?
3.
Yeah, so it is a different number of bars.
Yeah, so n minus
Yeah.
1 C3 is what I'm saying.
Okay. So yeah, that's great that you can see that. So one conjecture is that the number of quadruples for n is n minus 1, choose 3. So if you're not seeing this or if you don't get where it comes from, then I would suggest thinking about what we did previously. I don't expect, I mean, like, of course, if the last truth session was the first time you're looking at binomial coefficients, it might take some time to get used to them. But maybe you can try to see whether this is true, see for the first few values of n, whether it actually matches this number or not. So does anyone have any other answers or guesses or something like that? So Anantajit, do you have something different to say?
Sir, I actually have an idea to generalize it for any some suppose k numbers.
Okay, that's great.
That
And can you quickly tell me what your answer for that would be?
well, sir, it would just be n minus 1 choose k minus 1.
Okay, great. So it's great that you have that idea in mind. Yeah. So of course, that is what, like, at the end, that is the final thing that we would like to write. So let me just, but no, maybe let me not write that down. Let us stop today with just the quadruple thing, just in case, so that everyone can take some time to digest all this stuff. So, Vikrant, do you want to say something else about this quadruple thing, or are you?
So the same thing most likely.
Okay.
Same thing only.
Okay. Then, Madhusudan, do you want to say
Sir, but we
something
can just,
different, or?
sir,
Yeah,
we
sure.
can, sir, but
Yeah.
but we can prove it like similarly how we prove we can the other way of saying it I just don't know how I need to calculate it well, but we can prove it how we prove the square the triples thing using the pairs thing. We can use prove the quadruples thing using the triples thing. If we want to find that way, if we want it that way, then we can prove it like that.
Okay, so I would, I mean, if you are, if you like that way, then you can try
I like
and
both
see what you
ways.
get.
I like both
Yeah,
ways.
then try both ways and see whether you get the same answer for both, or yeah. Okay, so Madhusudan, do you want to say something, or?
Sir, I wanted to repeat whose fact, Anantajit's fact, sir.
Okay. Yeah, sure. I mean, if you see that directly, that is great. But even if you don't, like, for example, if you don't really get why this is true, that the number of triples is n minus 1, choose 2, I would suggest that you think about these balls and bars some more. Especially if it is the first time that you are seeing this, I would not expect that you immediately quickly understand what is happening. But if you have seen binomial coefficients before, I mean, that saved me some work, that not having to talk about binomial coefficients. But hopefully, if you can understand binomial coefficients, then you think about these, what exactly these bars are representing, what these balls are for, then hopefully this will make sense with a bit of thought. Okay. And then the next question is, of course, once you understand these triples, try to do for quadruples. And if you have the time, try to generalize it to, like, okay, 5 numbers, 6 numbers, and so on. Okay. So with that, we will stop for today. And also, like, I mean, at least it seems like there are a lot of you who already know about binomial coefficients and so on. Then I would definitely suggest looking at the drive link that I sent, the problems there, because those are more challenging and probably require a bit more thought. Okay, so I guess we can stop here, and if anyone, uh, I mean, if anyone has any questions, you can ask me, but I mean, the time is officially over, so you can, of course, leave. And
Does anybody have any doubts? I think no. We can end over the meeting as the time is also ended.
yeah.
Yeah. Okay. Bhairav, hello.
Yes. No.
Yes, I think we should end the meeting.
Okay.
Yeah.
Just a second.
Okay then.
Okay. Bye,
Thank
sir.
you, sir.
Flawless lecture.
Thank
Yeah.
you,
Bye,
sir.
sir.
Thank you,
Thank you, sir.
sir.
Thank
Bye,
you,
sir.
sir.
Thank you, sir.
Thank you,
Bye.
sir.